A field of a charge can be observed when a positive test charge is added. As you can see, the test charge is repelled each time it is placed around the charge. This means that a field is positive as there is a repulsive force between the two like charges. The same concept is applied to a negative charge. However, the noticeable difference is that the force will be attractive. This force will be the same magnitude, but to express the opposite direction, the magnitude can be said to be negative, and thus the vector field quantity will be in the opposite direction.
Potential is the amount of work needed to bring a charge to a point in an electric field. It takes the same amount of work to pull a charge to one spot of a given radius on the curve as it does to pull it out to a different spot on the curve. That means that the work done per unit of charge, the electric potential, is also the same. Therefore, we are able to plot out equipotential lines.
When two opposite charges are placed, we can observe their interaction between the two fields when a positive test charge is placed. We can break this down into the repulsive force between the test charge and the positive point charge, and the attraction force between the test charge and the negative point charge. As you can see, by plotting the path of the test charge, we can begin to plot out the pattern of the field.
When two like charges are placed, we can observe their interaction between the two fields when a positive test charge is placed. We can break this down to the repulsive force between the test charge and the positive charge, and the other repulsive force between the test charge and positive charge. As you can see, by plotting the path of the test charge, we can begin to plot out the pattern of the field.
When the ball is placed here, we can see the two vectors to get the resultant field for the specific point. This can be repeated. As you can see, the shape of the field will begin to look like this. Finally, the interaction between the two fields will look like this.
To calculate electrostatic forces, we will need to determine a few things first. Let's take the force of a negative point charge and a positive test charge as E1. We can calculate E1 by taking Coulomb's constant, which is 8.99 times 10 to the power 9, multiplied by the magnitude of the point charge divided by the distance between the positive test charge and the point charge squared. In the formula, it will look as such. The same can be done with the positive point charge. However, as force is a vector quantity, this will be expressed in the opposite direction, as positive like charges repel. Now that you understand this, we can take this a step further. If we want to determine the force between two opposite charges, we must first understand that the two are exerting the same force on each other. To determine the force, we can place a positive test charge. Using this positive test charge, we can determine E1 between the test charge and the negative point charge using the equation we learned before. However, if we want the force between the two point charges, we will have to multiply the magnitude of the positive point charge by E1. This will determine the force between the positive point charge and the negative point charge. Now, if we take this scenario where we have 3 point charges of different magnitudes, we must determine the resultant force and figure out where the positive test charge will go. It may seem slightly complicated at first, but the best way to approach this is to break it down to what we have learned before. If we individually look at how the positive test charge is affected by the point charges, we can see that it becomes much easier. We can determine E1, which is the force between the positive test charge and the positive point charge, by substituting the values into the formula we learned before. We can repeat this by finding E2, which is the force between the test charge and the negative point charge. Remember that this is an attraction force rather than a repulsion force that we did before. If we do this again for the second negative point, we can plot all the forces together. Now let's substitute in example values, 4, -2, and -3. We can determine the resultant force using two different methods. If we draw out each vector, we can determine the value of the dotted line. Or we can add up each vector, and with that we will get the vectors of the resultant force. If we use Pythagoras' theorem, we can determine the resultant force, as shown below. However, we are still not finished. Using trigonometry, we can determine the angle at which the test charge moves. Finally, we can say that the positive test charge moves with a force of 3.61 newtons, and at an angle of 56.3 degrees.